Welcome to The Explainer. We're all about breaking down big, complex topics, and today we are tackling a huge one, machine learning. So let's just jump right in with the big question, right? What's really the difference between a computer just doing what it's told and a computer that's actually learning something new? It's a huge distinction, and it's at the core of everything we're about to talk about. All right, Section 1, Beyond Programming. What's learning? To really get this, we've got to look past how we normally think about computers. This isn't just about coding line by line. It's something else entirely. Okay, so here's maybe the best way to think about it. Traditional programming is like a super strict recipe. You follow the steps perfectly, you get the exact same result every single time. It's what we call a deterministic system, totally predictable. But machine learning, that's more like a chef who's learning on the job. They're not following a recipe, they're developing their own rules based on experience. It's a probabilistic system. It doesn't give you a 100% guarantee, it gives you its best guess, its probability of being right. Yeah, I know. That definition looks pretty dense and academic, right? But if you boil it down, it's actually super simple. It just means a computer is learning when it gets better at some job just by getting more experience. Think about your spam filter. No one is sitting there writing a new rule for every single junk email. The system just sees more and more examples. That's the experience, and it gets smarter at spotting spam all by itself. So next up, Section 2, the secret is finding patterns. Okay, but how does it get better? Is it magic? Nope, not at all. The entire secret, the whole trick, comes down to one thing, finding patterns. I mean, think about it. So much of what we call knowledge or even intelligence is really just recognizing patterns. You see a face, you recognize a friend. You hear a voice, you know who's talking. That's all pattern recognition. And that's the whole idea here. If you can't explicitly program something, like how to recognize a cat, maybe you can just give a computer a ton of examples and let it figure out the pattern for itself. And computers are ridiculously good at finding patterns in huge piles of data, even ones we'd totally miss. All right, let's make this real. Section 3, Learning to See an Example. We're going to walk through a classic example to see exactly how this works in practice. So here's our goal. Let's teach a machine to classify fruit. Specifically, can it tell the difference between an apple and an orange? And to do this, we're going to use one of the most common methods out there, something called supervised learning. Just think of it like a student with a teacher. Okay, so how does this teaching actually work? It's pretty much what you'd expect. First, the teacher, that's us, shows the algorithm an image of an apple and gives it the label apple. Simple enough. Then we show it an orange and we label that not apple. Now, one or two examples isn't enough, right? So step 3 is just giving it tons and tons of data, hundreds, thousands of labeled pictures of apples and oranges, and then the magic happens. The student, our algorithm, starts to find the pattern. It analyzes all that data, the colors, the shapes, and it starts to figure out for itself what the rules are that separate an apple from a not apple. And this is the result of all that training. The machine has created what's called a decision boundary. It's basically the rule that it came up with all on its own. It's like an algorithmic line in the sand. If it sees a new piece of fruit, it checks its features, how red is it, how round is it, and if it falls on one side of that line, bam, it's an apple. If it falls on the other, it's not. And this, right here, is the whole point. This is the goal. By seeing all those examples, the algorithm can generalize. That's the key word. It can use what it's learned, its new rule, to make a really good guess about data it has never, ever seen before. And that's the huge leap, right? That's the difference between just memorizing stuff and actually learning. Okay, Section 4, 3 styles of machine learning. So what we just saw with the apples and oranges, that was a perfect example of supervised learning. But that's not the only way machines can learn. There are actually 3 main styles. So let's zoom out and take a look. So here are the big 3. First, you've got supervised learning. That's what we just did. It's learning by example from data that we've already labeled. It's great for things like classification. Next, there's unsupervised learning. This is where it gets really interesting. Here, the machine is learning by discovery. You just dump a whole bunch of unlabeled data on it, and its job is to find the hidden patterns, all by itself, to find the clusters. And finally, you have reinforcement learning. This is learning by trial and error. You can think of it like training a dog. You give it rewards for good actions. It's amazing for teaching an AI to master a game or for robotics. Let's move on to Section 5, the never-ending hunger for data. Now, all 3 of those styles, they're pretty different, right? But they all share one thing in common. They are incredibly hungry. And that leads us to probably the single biggest challenge in all of machine learning. And that challenge has this awesome, very dramatic name, the curse of dimensionality. It sounds complicated, but the idea is actually pretty straightforward. The more variables or dimensions you ask your model to think about, the more data you need. And not just a little more, but exponentially more. Back to our fruit example, right? We just used 2 dimensions, color and shape. But what if we add texture and weight? Each new feature you add makes the space the machine has to search through way, way bigger, and you need a ton more examples to fill it in. And that's why you always hear that machine learning just eats up data. There's this rule of thumb that you need at least 5 training examples for every single dimension in your data. Now, that doesn't sound too bad for our 2-dimensional fruit problem. But what about a model for, say, facial recognition? You might have hundreds, even thousands of dimensions. The amount of data you need just explodes. It becomes absolutely astronomical. Data really is the fuel that makes this whole engine run. So when you strip it all away, what's the big takeaway? Machine learning isn't some kind of magic. It's just a profoundly powerful tool for finding patterns, a tool that runs on data. And because of that, it lets us solve problems that we could never, ever solve by writing rules by hand. Which leaves us with one final, kind of exciting question to think about. As machines keep learning from more and more of our data, where is their next big aha moment going to come from? What will they see that we can't?